Tchebycheff inequality. If we know the probability distribution of a random variable x, we may compute E of x and variance of x. Conversely, if E of x and variance of x are known, we cannot construct the probability distribution of x and hence compute quantities such as P of modulus of x minus E of x less than or equal to k. Although we cannot evaluate such probabilities from a knowledge of E of x and V of x, several approximation techniques have been developed to upper and or lower bounds to such probabilities. The most important of such techniques is Tchebycheff inequality. Statement: if x is a random variable with E of x equal to mu and variance of x equal to sigma square, then 1. P of modulus x minus mu greater than or equal to c less than or equal to sigma square by c square for any c greater than 0. 2. P of modulus x minus mu less than or equal to c greater than or equal to 1 minus sigma square by c square for any c greater than 0. Alternative forms. If we put c equal to k sigma, where k greater than 0, then Tchebycheff inequality takes the form P of modulus x minus mu divided by greater than or equal to sigma less than or equal to 1 by k square, or P of modulus x minus mu divided by k less than or equal to sigma 1 minus 1 by k square. Problem 1. A random variable x has mean mu equals 12 and variance sigma square equals 9 and an unknown probability distribution. Find P of 6 less than x less than 18. Solution. By Tchebycheff's inequality, P of modulus x minus mu less than or equal to c greater than or equal to 1 minus sigma square by c square implies that P of minus c less than or equal to x minus mu less than or equal to c greater than or equal to 1 minus sigma square by c square implies that P of mu minus c less than or equal to x less than or equal to mu plus c greater than or equal to 1 minus sigma square by c square. Given mu equals 12, sigma square equals 9. P of 12 minus c less than x less than 12 plus c greater than or equal to 1 minus 9 by c square. Putting c equals 6, we get P of 6x less than 18 greater than or equal to 1 minus 9 by 36. P of 6x less than 18 greater than or equal to 3 by 4. Problem 2. If the random variable x is uniformly distributed over minus root 3 to root 3, compare P of modulus of x minus mu greater than or equal to 3 sigma by 2 and compare it with the upper bound obtained by Tchebycheff's inequality. Solution. Uniform distribution PDF, f of x equals 1 by b minus a less than x less than b, mean equals b plus a by 2 and variance equals b minus a whole square by 12. Mean equals mu equals root 3 minus root 3 by 2 is equal to 0. Variance equals sigma square equals root 3 plus root 3 whole square by 12 is equal to 1. That is mu equals 0, sigma square equals 1. Therefore, P of modulus of x minus mu greater than or equal to 3 sigma by 2 tongue poking smiley of modulus of x greater than or equal to 3 by 2 equals 1 minus P of minus 3 by 2 x less than 3 by 2 equals 1 minus integral minus 3 by 2 to 3 by 2 1 by 2 root 3 dx equals 1 minus 1 by 2 root 3 into x limit minus 3 by 2 to 3 by 2 equals 1 minus 3 by 2 is equal to 0.134. By Tchebycheff's inequality. P of modulus of x minus mu greater than or equal to k sigma less than or equal to 1 by k square. P of modulus of x minus mu greater than or equal to 3 by 2 less than or equal to 4 by 9 is equal to 0.444, which is a poor upper bound. Problem 3. Can we find a random variable x for which p of mu minus 2 sigma less than or equal to x less than or equal to mu plus 2 sigma equals 0.6? Solution. Given p of mu minus 2 sigma less than or equal to x less than or equal to mu plus 2 sigma equals p of modulus of x minus mu less than or equal to 2 sigma. By Tchebycheff's inequality, p of modulus of x minus mu less than or equal to k sigma greater than or equal to 1 minus 1 by k square implies that p of mu minus 2 sigma less than or equal to x less than or equal to mu plus 2 sigma greater than or equal to 1 minus 1 by 2 square equals 0.75. Therefore, there does not exist a random variable x satisfying the given condition. Problem 4. A discrete random variable x takes the values minus 1, 0, 1 with probabilities 1 by 8, 3 by 4, 1 by 8 respectively. Evaluate p of modulus x minus mu greater than or equal to 2 sigma and compare it with the upper bound given by Tchebycheff's inequality. Solution. Given x equals x takes value minus 1, 0, 1. P of x equals x1 takes value by 8, 3 by 4, 1 by 8. E of x equals minus 1 into 1 by 8 plus 0 into 3 by 4 plus 1 into 1 by 8 is equal to 0. E of x square equals minus 1 whole square into 1 by 8 plus 0 into 3 by 4 plus 1 square into 1 by 8 is equal to 2 by 8 is equal to 1 by 4. Variance of x equals e of x square minus e of x whole square 1 by 4 minus 0 is equal to 1 by 4. Therefore p of modulus of x minus mu greater than or equal to 2 sigma equals p of modulus of x minus 0 greater than or equal to 2 into 1 by 2 equals p of modulus of x greater than or equal to 1 equals 1 minus p of minus 1 x less than 1 is equal to 1 minus p of x equals 0 equals 1 minus 3 by 4 equals 1 by 4. By Tchebycheff's inequality, p of modulus of x minus mu greater than or equal to k sigma less than or equal to 1 by k square implies that p of modulus of x minus mu greater than or equal to 2 sigma less than or equal to 1 by 2 square equals 1 by 4. The two values coincide.
Problem 5. A fair die is tossed 720 times. Use Tchebycheff's inequality to find a lower bound for the probability of getting 100 to 146s. Solution. Let x be the number of sixes. P equals P of getting 6 in a single toss equals 1 by 6. Q equals 5 by 6 and N equals 720. X follows a binomial distribution. Thus, mean equals NP and variance equals NPQ. Implies that mean equals 720 into 1 by 6 is equal to 100 and variance of x equals 720 into 1 by 6 into 5 by 6 is equal to 100. By Tchebycheff's inequality, p of modulus of x minus mu less than or equal to k sigma greater than or equal to 1 minus 1 by k square implies that p of modulus of x minus 120 less than or equal to 10k greater than or equal to 1 minus 1 by k square. Implies that p of minus 10k less than or equal to x minus 120 less than or equal to 10k greater than or equal to 1 minus 1 by k square. Implies that p of minus 120 minus 10k less than or equal to x less than or equal to 120 plus 10k greater than or equal to 1 minus 1 by k square. Putting k equals 2, we get p of 100 less than or equal to x less than or equal to 140 greater than or equal to 1 minus 1 by 4 is equal to 3 by 4. Problem 6. Use Tchebycheff's inequality to find how many times a fair coin must be tossed in order that the probability that the ratio of the number of heads to the number of tosses will lie between 0.45 and 0.55 will be at least 0.95. Solution. Given p of 0.45 less than or equal to x by n less than or equal to 0.55 greater than or equal to 0.95 equation 1. Let x be the number of heads. Then x follows a binomial distribution. That is x approximately b of np, square root of npq, where p equals q equals 1 by 2. Therefore, x by n approximately b of 1 by 2, 1 by 2 root n. By Tchebycheff's inequality, p of modulus of x by n minus 1 by 2 minus c greater than or equal to 1 minus sigma square by c square. P of 0.5 minus c less tha or equal to x by n less than or equal to 0.5 plus c greater than or equal to 1 minus 1 by 4 n c square. Putting c equals 0.05, we get p of 0.45 less than or equal to x by n less than or equal to 0.55 greater than or equal to 1 minus 100 by n. Equation 2. Comparing equations 1 and 2, we get 1 minus 100 by n equals 0.95, implies that 1 minus 0.95 is equal to 100 by n. N equals 100 by 0.05 implies that n equals 2000. Problem 7. A random variable x is exponentially distributed with parameter 1. Use Tchebycheff's inequality to show that p of minus 1 less than or equal x less than or equal 3 greater than or equal 3 by 4. Find the actual probability also. Solution. For exponential distribution, PDF, f of x equals lambda e power minus lambda x, x greater than or equal to 0. Mean equals 1 by lambda and variance equals 1 by lambda square. Here lambda equals 1. That is mu equals 1 and sigma equals 1. By Tchebycheff's inequality, p of modulus of x minus 1 less than or equal to 2 greater than or equal to 1 minus 1 by 4. Implies that p of minus 1 less than or equal x less than or equal 3 greater than or equal 3 by 4. To find actual probability, p of minus 1 less than or equal to x less than or equal to 3 equals integral 0 to 3 e power minus x dx equals minus e power minus 3 limits 0 to 3 equals 1 minus e power minus 3 equals 0.9502. Problem 8. If x denotes the sum of the numbers obtained when two dice are thrown, obtain an upper bound for p of modulus of x minus 7 greater than or equal to 4. Compare with the exact probability. Solution. S equals 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. X equals the sum of the numbers obtained. X takes values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. P of x equals x takes value and 1 by 36, 2 by 36, 3 by 36, 4 by 36, 5 by 36, 6 by 36, 5 by 36, 4 by 36, 3 by 36, 2 by 36, 1 by 36. E of x equals 2 by 36 plus 6 by 36 plus 12 by 36 plus 20 by 36 plus 30 by 36 plus 42 by 36 plus 40 by 36 plus 36 by 36 plus 30 by 36 plus 22 by 36 plus 12 by 36 equals 7. East of square equals 4 by 36 plus 18 by 36 plus 48 by 36 plus 100 by 36 plus 180 by 36 plus 294 by 36 plus 320 by 36 plus 324 by 36 plus 300 by 36 plus 242 by 36 plus 144 by 36. Equals 1974 by 36. Equals 329 by 6. Variance of x equals e of x square minus e of x whole square equals 35 by 6. By Tchebycheff inequality, p of modulus x minus mu greater than equal to c less than or equal to sigma square by c square implies that p of modulus x minus 7 greater than or equal to 4 less than equal to 35 by 96. Now, p of modulus x minus 7 greater than or equal to 4 equals p of x equals 2, 3, 11 or 12 is equal to 1 by 36 plus 2 by 36 plus 2 by 36 plus 1 by 36 is equal to 1 by 6. There is my difference between the two values.